to hear this talk. So, all right, Greg, take it away.
Cool, cool. All right, thanks, Greg. Let's see if I can share my screen here. Nope, that's the email. Let's not share that. Okay. Cool. Well, thanks everyone for coming to this. So this is hopefully going to be a nice, easy, not too complicated talk. And I'm going to be talking about reproducibility. And my talk is titled Everyday Reproducibility to emphasize that hopefully this is a practical approach to some of these problems. I stole this title from Johan, who he and I kind of worked on this together. So I thought I would start off by talking about what reproducibility is what I'm going to be talking about today, as opposed to what other people might talk about here. So I'm always a bit wary about these working groups getting together and defining things, because no one ever agrees on definitions. Nonetheless, for this talk, I'm going to go with the definition by some of the national academies who got together and wrote a report on reproducibility. And their definition of reproducibility was, well, they have two definitions. They have reproducibility and they have replicability. And their definition of reproducibility was, if I take your data and your code, and I take it from your computer and I put it on my computer and I run it, I should be able to
Okay, seems like Greg is frozen.
Yeah, that's what I see too.
Actually, Greg is gone now. Hopefully he's coming back in.
I think he'll be right back since he's actually gone.
Hope so.
I'll email him just in case.
Oh, I think I'm back. Am I back?
Yeah, you're back. You cut out right when you were defining
Can't hear
reproducibility.
anyone.
Yeah, I got reproducibility and replicability, and you were pretty much through reproducibility.
All right, let's see. Oh, can you hear me now?
Yes.
Okay.
Yeah, you're good.
Sorry. Well, that was exciting. Okay. All right. Let's try this one again. Okay. So, boy, let's share my screen here. Hopefully this is not going to be an issue. So I'm not sure where I cut off there, but giving my definitions here of reproducibility and replicability. And so the idea being that replicability is kind of the harder problem in some ways, where it would be, for example, I read someone's paper, they plated cells in some way, image them, and analyze them in some way. So I take my own cells, I plate them, I image them, I analyze them in some way, and try to answer the same question, hopefully get the same answer. So I'm interested in both these problems. In this talk, we're going to focus on the first, which is reproducibility, or kind of computational reproducibility. And so some people have seen some of the previous talks I've given, some of the normalization stuff I've talked about can be interpreted as kind of replicability here. But we're going to focus on computational reproducibility. And why we're going to focus on computational reproducibility is because I'm a statistician. So my kind of educational background is math, CS, and stats. And actually, as an undergrad, I was a CS major before I was a math major. And so I care a lot about this stuff, and particularly coding. And my kind of not so veiled goal here is to increase discussion about coding in science, because I feel like oftentimes it gets short shrift. And in reality, you know, people will write math in their papers, but the final arbiter of what the actual analysis is the code. And sometimes the code matches the math, sometimes it doesn't exactly match the math. And I feel like, this is my kind of rant here, is that there's not a lot of credit given for talking about what is actually kind of important here, which is making sure the code is right. So obviously I'm a statistician, I'm not a bench scientist. And so me talking about replicability is not quite, you know, the right thing for me to do. I don't really have kind of standing there, but I am, as a statistician, you know, we take data through code for results. And so I spend a lot of time thinking about that. In particular, the stuff I'm going to present in this talk came about kind of through some of the ideas we put together for the 2020 MIDAS Reproducibility Challenge. So MIDAS is the Michigan Institute for Data Science, and they ran a 2020 Reproducibility Challenge, and we submitted some of the ideas here to that, and won one of their categories, and we've subsequently turned this into a manuscript to try to educate people on some of these ideas. So we're talking about computational reproducibility, and computational reproducibility may seem like kind of a low bar, right? So basically what I want to talk about is, if I take your code and your data from your computer, put it on my computer, it should run. Now, the American Statistical Association and others have noted, so they say, this might sound easy, but practically this actually can be quite a difficult problem sometimes. It's not always easy to achieve what kind of the seemingly minimal standard. And in some ways, computational reproducibility is the easier challenge of the kind of reproducible, replicable universe out there. But in some ways, it's actually solvable, and we can actually solve this problem, and we have the tools to solve some of these issues. And so while making results replicable across kind of wet lab work is quite difficult, making sure code runs is totally solvable. So broadly, while this may seem like a low bar, it's not actually that easy. And the challenges that people face is, first of all, can we actually run the code? So if I think many of us had the experience, I've certainly had the experience of, you go out, you find a paper you like, you want to see what they did, you download their code, you try to run it, it doesn't work. You try to make it run for several hours, you can't get it to work. And it's maybe horribly written, it's just this disaster. And this is a common experience, I think, in kind of these data analysis circles. You know, so there are all sorts of issues that we can run into. Oh, they use this version of the software, I use this version, they have this version of the operating system, I have this version, they use this language, I use this one, or this dependency of dependency of dependency isn't installed, it needs some specialized software, it can't run on this. And theoretically, some of these issues are kind of solvable. Theoretically, you should be able to get these things to run, but practically, getting these things to work can be this kind of black hole of time, energy, frustration, and it's not always clear it's kind of feasible to do or really worth the effort to do for some of these things. So the primary challenge is, can we actually get this stuff to run? Secondary challenge is, if I have code that can run, can I understand what it's doing at all? And so obviously, we don't want to require that people be able to read and understand code on kind of a line-by-line basis. That's what computers are for. And we're not software engineers. There's not a lot of credit given in the scientific community for writing nice code that works well, unfortunately. I would like to change that, but that's the way it is. But we'd like to have some ability to kind of go into someone's code, vaguely understand the structure of it, modify it, play with the parameters. Oh, can I change your tuning parameter? Can I change your threshold? And I want to see the output from your code when I do that. And so I can kind of pressure test or test the robustness of your code and play with things and see if what happens. I mean, this would be a great thing if we could do this in peer review. Obviously, there are challenges, one of them being that it's hard to even run other people's code. The second kind of point here with this is that often we want to be able to find reasonable entry points into analysis. So if you have all your analysis on one line in one file, it's not readable. It's hard to find how to get into this thing. It's hard to find how to run it. So we want to be, what we want to do is encourage tools that can help people do this in a practical way, rather than lecturing people about, you know, ways to organize their code and their data that people don't have the time to really absorb into. So that's the challenges as I see them. So our goals are, we want to be able to, for kind of computational reproducibility, is we want to be able to take an analysis and reproduce it, soup to nuts, raw data to output. We want to make sure the code is kind of accessible, understandable, and we can play around with it, we can experiment with it, and pressure test it to see what's going on. We want to make sure it's shareable, and above all, we want to make sure that this is practical. We can actually use this every day. So the goal here is, one of my kind of secret goals here is to convince you that some of these tools you can today go and use to, you know, make analysis reproducible in a really, really nice way. So the strategies that we're going to be kind of employing to solve these issues are the ones that I've found useful in particular are, first, something called code containerization. And in particular, we're going to focus on some software called Docker, which can do this for us. And then the second one is kind of a code format, and which I'm going to call generally code notebooks. And in particular, I'm going to be talking a little bit about just an example, one called Jupyter, and a particular plugin called JupyText for writing code notebooks. So the first, so these kind of correspond to our two problems. Code containerization hopefully will make code actually run without exception. And the code notebooks are hopefully going to encourage us to write code that is easy to understand and play around with. Okay, so what is code containerization? Code containerization is basically what we're going to do is, so on the left here, I have some original computing environment. I've done my analysis in my computing environment. What I can do, so this is, you know, my computer, it's the software, my data, my code, the structure of my directories. Yep.
I'm still seeing your slide with reproducibility and replicability. Is there another slide?
Oh, boy.
I was wondering about that.
Yeah. Someone should have yelled at me a while ago. All right, let's try this again. Man.
Well, we figured you're just talking extemporaneously and didn't need slides.
I am talking extemporaneously.
We started pointing at stuff.
I almost gave you the speed up sign on my.
Oh, that's so funny.
Yeah.
Oh my God. Okay. So can you see me now? Yes.
Oh my goodness. Okay.
Yes.
Okay. Well, I mean, nothing's really that important besides what I say, as most of life. So you can see now I'm changing slides. Is that all good?
Yeah. Got it.
Okay.
You said that, right?
Yeah, I said all of this. None of it's super important to see the text. I was reading the text off of this. So so our two strategies here are, definitely yell at me if something's not matching up. I'll pressure test this as we go along. But our two strategies are code containerization and code notebooks. We need to maybe make my next talk should be about video conferencing software that actually works, maybe. So, okay. Okay, so here is our first strategy, which is code containerization. So you should see a nice little picture here. On the left here, I have my original computing environment. And so it's my code, my data, organization. It's basically my computer, right? And I can use this containerization software basically to encapsulate this environment into a file. So my first step here is containerization, which creates what's called an image file. And an image file basically compresses down my whole computing environment into a file on my computer. It's a file like any other file, like a Word file, like anything else. I can share my file. I can upload it to the cloud. I can put it on Google Drive. I can email it to my friends. And they can take it and they can download it. And when they run this file, it will basically boot up a copy of that original computing environment. So it will create basically a virtual computer set up exactly how I had my original computer set up to do that original analysis. So it will have my data, my code, all in the right places. It will not only have the files, but it'll have an installation of the software. If I used R on my original computer, it will have an installation of R to run the code. And
Are
so
there
it's, yep.
issues with this being proprietary? Like if I did something in MATLAB, I'm assuming MathWorks would not want me to share MATLAB with the world.
Yeah, so that's a caveat. Now there are yes. So I'm going to talk about that way at the end. So yes, so the limits here are, well, the limits, data limits are not that bad to deal with because you don't have to upload this anywhere public. You could share the file internally among your friends. So if the data is proprietary, you can share it in whatever proprietary way is allowed through this. Proprietary software, MATLAB, there claims they have a way to make this work. I have not tried it myself, but yes, this works better with open source stuff that you can actually share freely. In general, I'm trying not to be a snob about programming languages. I will say that one of the issues with MATLAB is obviously it's behind a paywall, which hurts reproducibility, and this is a direct way that it hurts reproducibility. Nonetheless, I understand everyone has things they like. Theoretically, MATLAB says you can do this, but I haven't actually personally tried it. Any other questions about?
Is this the DMG file, or is it some other thing? Like on a Mac, would this be just what we call an image on the Mac operating system?
So it's slightly different. I don't even know what the weird format they use for this is, but it's basically just a single file. So it's like any other file, and it more or less compresses it down. Yeah. Other questions? So it's yeah. No, yeah. Okay. So
Yeah, actually, I did have another question. Is it making enough of a copy? Like this is R. If the third party didn't even have R installed, could they still run this container?
Absolutely. Yep.
Okay.
Absolutely.
Yeah.
So it literally has everything that you need, and so it is a one-stop shop. Makes things absolutely reproducible, pretty much without exception. And because it is containing, you can put anything you put on a computer, you can put in an environment like this. You can containerize up. So yeah, it's not only just containerizing code, it's containerizing a whole computer and sharing it. So basically, so this is kind of in words what I said here. Should be on slide 8 now. So it's not actually particularly new technology. Some of the stuff has existed. This containerization is the newest incarnation of it, and it is a particularly slick incarnation because it is very fast. So what they're doing is actually only really encapsulating the high-level part of the operating system and the code and the analysis and stuff, and they're reusing some of the low-level stuff, which means it's actually relatively small on disk. It's really fast to start. It's not like you have to boot up a whole second computer and wait 15 minutes for it to boot up. It pretty much instantaneously starts up, and it runs basically at the native speed of whatever computer you're running it on. And the reason is basically it's not really starting a new computer. It's just tricking your computer into thinking it's on a different computer. So it's basically changing the name references. It's what's called the namespace and some other things in kind of computer science lingo. So I thought what would be useful here is to look at an example. And in particular, I built a little example to show. One of the places many of these images are shared is called Docker Hub. So the software we're using is called Docker. And you can share these on what's called Docker Hub, which is just a repository for sharing this stuff. So let me see if I can go over there. Boy, I'm gonna have to reshare my screen, aren't I? Okay, let's try this. Let's just share the whole screen here. Let's see if I can minimize this whole thing. Okay, so you should be able to see I'm on docker.com. Is that, everyone can see this?
Yes, we see.
Okay, so there's Docker Hub where people host these images. Now you don't have to. If you have proprietary data or something, you don't have to put it on here. Docker Hub has, I don't know, it probably says somewhere how many millions of images they have, but it has a whole bunch of pre-built images. So for example, if I want to do an analysis in Python, I could work off of their Python image. So here's a basic computer set up with a Python installation. If I wanted to work with R, I could look up to something called Rocker, which is a version, a computer set up with R installed and some of the nice things set up there. But you can upload your own stuff. So if I look up myself here, I have some stuff on here. Here's an image called MWE, minimum working example. It's an image I set up to kind of demonstrate. So I've made this image, I've containerized some computer with some analysis, I've uploaded it here, and you can just download it and run it. And so why don't we do that? Okay, so you should see my terminal here now. And if your eyes are going to gloss over at typing commands into a command line, hold tight. We will talk about how this can be all done interactively. So you don't have to really fiddle with a command line too much. In fact, the Windows version of this has a really nice interactive version, but you can interactively do this. But I'll show you the real basics. So I have my image, and I'm going to download it. So I say Docker pull, I download my image, downloads the image. I want to run this image, so I say Docker run, and I give it the image name I downloaded, my minimum working example. I'm going to give it a couple more flags, IT for interactive. Don't have to worry about it too much now. I'm going to give it a name called example, and we'll see why that's useful. And I run it, and instantaneously it starts up. So what you should see is that my prompt here has changed from my desktop prompt to this other horrible prompt. I'm now in the container. I'm not actually really on my desktop, as it were. I'm in the container. If I type ls, I can list what's in my container, and I have containerized an analysis script and a data file. And this is a kind of fully working operating system here with analysis script and data file. And as Leah asked, I have an installation of R. If I type R, it boots up an installation of R. This installation of R is running from the container. So I don't have to have R installed on my computer. It comes with the container. I don't have to have the correct version or the correct dependencies. All of that can be encapsulated up into this file that can be shared. And so if I want to run my analysis, I can say R script, I can give it my analysis file, I can run it, and if I list my directory again, now I have a plot output. So my analysis script was just reading the data and plotting it in some way, right, in this kind of simple example. So that's the example. It's really dead simple, first of all, to use someone else's containerized analysis. Download it in one command, run it with one other command, and you're dropped into a kind of fully working instantaneously environment where everything has been set up. So I have the data, I have the analysis script, I have the software to run it on there, and I can run it in there. If after I've run it, I can leave my container, so I'm back on my desktop now, I could actually copy out, I can copy files to and from the container. So it's basically paused in the background now. I could say Docker copy, I'll give it my image name, it was example. In the analysis folder, it was our plots.pdf. I copy it to my working directory, and it will copy out my my plots.pdf. I'm just going to remove my container after I'm done with it, and now you should see I have my plot that I copied out that was run from the analysis in the container, and it is now copied out to my original computer. So that's kind of a typical workflow for this kind of thing. Cool. So what I'm trying to impress upon people is that it's really, really, really simple to do that. Let's see if I can start this up.
Quick question.
Yeah. Any other? Yeah.
Your R script. I'm assuming it's possible to look at the code while we're in there.
Oh yeah. So and we'll I'll get to that. So if people hate command line interfaces, you don't have to use it. I'm going to show you that you can use whatever normal kind of graphical interface. So that's just the real basics of it. And it's not going to let me go into slideshow, but I think that's okay. Let's just move some of this to the side here. Good enough. Okay. So, okay, so it should be. Technology is not really being nice to me today. Okay, let's hopefully get back to my slides here. Okay, so that was my example. Let me stop sharing for a second while my slides don't want to work with me. Okay, let's, oh, maybe this will work. Okay. I don't know. Where did Zoom go? Trying to impress upon you technology is easy, of course, by showing that it's not easy at all to work, right? Okay. So I showed my example. Super, super easy to use. Now, the question is, how hard is it to actually do this yourself? And to do it, you have to basically write a configuration file to set up that computer with your analysis, with your code, with your software that you want, which might seem really daunting. But the nice thing about the way that this has been built up is that you don't actually have to start from scratch. You can basically bootstrap off of existing images. So I showed you that there on Docker Hub, there were thousands of images out there, or at least I tried to impress that upon you, with kind of software pre-installed and configured. And so instead of starting from scratch and having to do low-level setting everything up in some awful way, you can basically, I could just go and I could go on Docker Hub and say, oh, I want, a Python installation with, this. I can go bootstrap off of their image, add on whatever data code, maybe install some particular packages that I need to have installed for my particular application, and Bob's your uncle, I have, a working container. So there's a whole bunch of really nice images out there they can basically bootstrap off of. So I'll just show you an example. So you should see some awful code now on the screen of a configuration file. So the top here is my configuration file. And it is 6 lines long. So it is really dead simple to do this. So the practical, this is just a really practical example of what it actually looks like to do this. So my first line, this from, basically says I'm going to bootstrap off this image. And you don't have to worry too much about it. It's giving me a version of R. It's giving me a setup container with R already installed. And so that does the majority of the heavy lifting here. After that, I just have to say, okay, I'm going to set up a working directory. I'm going to install a particular package that I like. In this case, ggplot2, and then I copy over my data, copy over my analysis, and then this last command just starts up a terminal. But that's all the more complicated it really needs to be. You might have some more commands copy over multiple files or multiple data sources, but you don't actually have to fiddle around trying to set something up in some complicated way, because for the vast majority of the kind of analysis you do, you just get some kind of base image that does the vast majority of the bootstrapping of things, and you just build on that. You add a couple lines of code to copy your stuff over. Down here at the bottom, I just have show you it's one command to build it, and it just creates the image file. You can share it how you want. So it's dead simple to actually build one of these two. Any questions before I proceed there?
Sudeep had a couple questions in the chat.
Let's see if I can access the chat. Show how bad I am at Zoom. Oh no. Chat.
I can unmute and ask you.
Yeah, that's fine.
Two questions. The first one is, how about the memory limit? Like, how much data can you put in there? Because you have to have your data in there, right? That's the first question. Yeah. And second question is, how about the parallel computing, right? Yeah. Does it support parallel computing?
Yes, great question. So the first one is, there is no limit. You can make whatever you want. You can put whatever you want in the file. It's just up to you. It'll make a big file if you have a lot of stuff in there, but you can put it as much as you want. If you upload it to a repository, say Docker Hub, they may have limits. I don't know. So it's going to be about how much you can actually kind of store. Does it? So that's the first one. Does it support parallel computing? There is another competitor to Docker called Synapse, which was built by, originally started by Lawrence Berkeley Labs. that is specific, basically does the same thing, but is made for parallel computing. And it's basically manages the permissions of software so that you can run it in some kind of parallel computing environment. So that is what I would recommend. If you really have a parallel computing requirement, then you should go with Synapse. But everything I said here, you change a couple keywords and it works basically exactly the same. So it's very similar. In fact, you can run Docker images on Synapse and Synapse images on Docker and back and forth. So yeah. So this stuff is not built for reproducible research. It's built for developing and deploying web applications mostly. So it's built by a bunch of software engineers who know what they're doing. It wasn't built by some schmuck like me. So it actually works pretty well and they're pretty slick. Other questions?
Yeah, I have one. So this, are you going to also talk about, well, how should I say this there? I really think this is cool, and I'm trying to reproduce what you showed us on my.
Yeah.
But what about the the issue of reproducing? Like basically, we just did this reproduction here without there being any human understanding of what was going on. So the old-fashioned kind of point of view is the mathematics is supposed to be the way that you communicate to someone else what you're actually doing in the computer. Does your talk address the issue of understanding what the code is doing? Is that like the next phase?
Yeah, sure.
Okay.
Yeah, it does a little bit. Yes, and unfortunately, so I'll have a link to our manuscript at the end. I'll have a shameless plug here, but yeah, that was one of the things we really wanted to talk about.
Okay.
We'll see how much we can get to it, but yeah,
Good.
Absolutely. Yeah. I mean, that's a much harder problem than the basic just sharing the code, making it run. But yeah. Okay. Any other questions? Okay, let's see if I can continue on. Okay. So I'm just gonna share it like this so I can go back and forth. So I understand that it's kind of command line interfaces aren't everyone's cup of tea, and in particular, I'm not going to advocate really for skirting around the command line interface, doing your analysis there. Nobody likes doing that. I don't like doing that. What I'm going to advocate for, Greg set me up nicely for this, is code notebooks, which are not particularly new. They kind of come around the past 10 years or so and become quite popular, maybe 5 years or so and become quite popular. But they are a really nice and natural way of interweaving code, commentary, and output all in a single file. And it's going to help us kind of promote some kind of logical structure, hopefully, to our analysis, so we can hopefully understand what's going on. And in particular, I'm going to talk about a particular format of this called Jupyter Notebooks and this kind of attendant software called Jupyter. And again, I guess I have this is only one slide, which is interesting. Well, I'm going to show you, let's just look at an example. So here is Jupyter. It's a development environment for writing notebooks. I'm sure many people are familiar with this. Some people probably aren't familiar with this. And what you can see is that I have commentary, including math, and code, more commentary, and more code. So I can kind of interweave all of these things in a single document. And there are other formats. There's something called R Markdown, which is popular among R. Jupyter is particularly popular among Python users, but they can be used for any language. It's pretty much a language agnostic. And so, for example, I can write some commentary. I can even write some math. I can render it, and I can get some nice kind of rich text kind of markdown of my commentary. But then I can also interleave, say, a code chunk. So maybe I'll read my data. Hell, maybe I'll even look at the top of my data. This is what my data looks like. I can have some other commentary. Let's do some plotting, and then I can plot it, and it will actually put the output in this same document. So there are many formats for this, but all of them kind of operate in the same way, where they've chunked up analysis in this way, which I think helps promote some kind of logical structure to your analysis. It allows you to include really rich annotation, and include the output along with it. So one of the reasons we like this is because you can, it makes it hopefully a little easier to jump in, view the structure of the code and jump into it and play with people's code. So for example, if I want to change, I can jump in and change the number of bins in my histogram and rerun it, and the output is immediate. I don't have to go find some file somewhere else where it's saved the PDF of the output. So it's not, not the most revolutionary thing in the world, but it's quite nice. Let's see where I am on my slides here. Let's see if my slides are actually going to work for once. Okay, let's just share my screen again. Okay, so let me find where I am in my slides. Okay, so you should see my slides now. So code notebooks are really nice. In particular, the one I've looked at there is called Jupyter from Project Jupyter. There are a couple of popular formats. There's a plugin called Jupytext, which I'm just going to plug here. People have different formats they like. If you use Jupyter, you can actually run this plugin, and it will simultaneously maintain mirrored versions in all the kind of popular formats. So if your friend likes R Markdown, I like Jupyter notebooks, or I like whatever script version, it will just maintain all of the analysis kind of real time in all of those. So when I encapsulate up or I containerize up my analysis, I can share all the versions, and people can use whatever version they want. And in particular, one of the nice things, if you notice when I ran, let's see if I can go back here, when I was running this notebook, this is running from my web browser. And so these IDE, these development environments these days basically run from the web browser. And one of the ways that's very, very powerful is that you can basically use it to get a interactive window into your containerized analysis. So here I got an image, let me just show it interactively. But basically what we've done, we've built not only a containerized version of our analysis, but we've built an interactive containerized version of the analysis. But again, my configuration file up here is again only 6 lines long. To get the interactive version, you just bootstrap off a more advanced kind of a more sophisticated base image, but it's actually not much more complicated. So we're bootstrapping off an image we built, which has interactive reproducible results. So I can go back, let's say, so you shouldn't be able to see my terminal now. I can say Docker, well, let me download it. So it's version 2, I'm just gonna append it to download version 2, and I can run it. I'm gonna give it a name, and there's one extra command, which is some magic I'm not gonna talk too much about, just so it works in my web browser nicely, and I just run my version of my interactive version. It's basically one line. I mean, you don't really have to understand it, you just have to copy and paste it in, and you can run it. So I run it, and it gives me a little prompt that says, please follow this into my web browser. So I can open this link, and it brings me to this nice splash page, right? So this is run from my container. This is an interactive window, basically. The web browser is on my desktop, but the back end is in my container. So I could browse the file contents of my container. I have my scripts in various versions, my data, I have a HTML, saved version of my output, for displaying my output if I wanted to display it on a web page or something. But I can also boot up. I have not only included the files and an installation of, say, R or something, or Python, I have also included a whole version of the software to do the analysis. So now I've booted up into Jupyter, the software to do the analysis. I can open up my notebook. But this all, while it's being used through my web browser on my personal computer, the back end of it is running from the container. So all these files are in the container. I can delete them, I can change them. It's all contained within the container. So all of this analysis here, if I want to write some math here, you can do whatever you want. You can play with the analysis in a fully interactive way, just through a web browser, like you would with any other analysis. But all of this is perfectly set up. I've already installed this package ggplot2 in my container, so that everything is kind of perfectly reproducible, and I can play with their analysis. So you can imagine you could share this with a collaborator or share this as part of a peer review process, and someone could actually go in and hopefully play with the code and actually assess it in a real-time way, rather than, say, forcing people to go download some awful code that doesn't run, that takes 5 hours to try to figure out. And no one's going to do that for peer review, or even for half the tools they want to use. So it's makes for a really nice way of providing an interactive interface to fully kind of encapsulated, perfectly reproducible analyses. Any questions at this point? Okay. Continue.
Quick question.
Oh, yeah. Sure.
So I haven't used Jupyter before. I've used Google's Collaboratory. Do you know that? Can you comment briefly on similarity?
I think it's really similar. I think their collab is pretty much Jupyter, if not exactly.
It's pretty much exactly the same.
Okay, yeah, around this. Yeah. So it's pretty much that.
Collaboratory to do our scripts?
Yep.
Okay.
Absolutely. Yeah, all of these formats, they're like Jupyter is built for Python, but you can write Octave, you can write probably can't write MATLAB for MATLAB reasons. You can write R, Python, Julia, anything, pretty much any of them. You can probably write C and Fortran in them if you really hate your life. But yeah, and same with there's R Markdown, which is another format. And I know MATLAB has their own kind of what they call like percent scripts or something, which is pretty much a similar kind of thing. So yeah. Oh, the other thing I should show from here is that, of course, if you don't like Jupyter and you like R Markdown, I'm just gonna shamelessly plug our thing here. There's other things in here. So there's RStudio is part of this. So if you don't like Jupyter and you like RStudio, I can boot up. I also have RStudio installed in here. So you can, and there are various versions of this. I can open up my analysis as an R Markdown file because I like that better. And I could run my analysis in here. So it gives you these kind of things, give you a really nice, you can do this and you can encapsulate a whole bunch of different ways to play with your analyses for whoever wants to kind of look at them. Okay. Other questions before I move on?
I have a question, Greg.
Yep.
So if you have very complicated interdependence of libraries and environments, then that makes the Docker file extremely huge because you have to download them all.
Yeah, it could. It depends on how, typically code libraries are quite small. It's really the data that, well, typically it's going to be the data that's
not for Python, you could have like,
it could. Yeah, it could. So I'll address this a little bit at the end, but yeah, that's one of the issues. They're not huge these days. The stuff, this image that I'm showing is say 5 gigs, something like that. So it's not so tiny that you can, put it on, trying to think. I mean, it is relatively small. You can put it on your phone. I don't know. It's not so tiny that you can make 1 billion of these and host them on Docker Hub without them complaining, let's say, but I'll address that a little bit at the end. So yes, it will depend on the size of your analysis. The very simple example I have is like 100 megabytes or something, so it's not that bad. But yeah, it's going to scale with what you have. Yeah.
Thank you. Thanks.
Other questions?
Yeah, I have a question or maybe comment. Since the analysis, for example, our code, you load like ggplot2, right? When the version changes, or like, for example, Python 2 or maybe Python 3 point something, and then the code basically does not work if the version changes. And in that case, even if your code is on Jupyter Notebook, or even if you have that documentation, like nicely documented documentation, because of that version difference, you will not be reproduce what other people did, right? How do you?
Right, so that is exactly the problem we want to solve here, right? So if I just give you a .py file, Python file, and I email it to you, you may have Python 2, I have Python 3, it doesn't run on my computer. If instead I take my stuff and I put it in a container with the Python file, And I've included a version of Python. Now, it is a exact particular version of Python. It's a computer, basically. And so if I run the analysis in that container, it will run. If it ran when you containerize it, it will run when you share the container with me, because the version of Python in the container is a fixed version at what you fix it at. So if you take it outside of that environment, yeah, it might not run. But if it's in the container, if you containerize it, you share the containerized analysis, it will perfectly run, right? So it's at least I can play around in that environment and verify what you've done runs there. If I take it outside of that, no guarantees. But so ultimately, yeah, there could be some issues, but it should run. Does that make sense to you?
Yeah, yes, that does. I was seeing like ggplot2 and RScript, and if these libraries go obsolete or something, and
Right.
if the analysis is dependent on those libraries, the problem, I think that does make sense. Yeah, thank you.
Right. So it could be that they go obsolete, but if I have containerized version of ggplot2, it exists in that container in perpetuity. It will exist there forever until I delete it. So even if they delete the code online, I still have a local version of it in that container. Now, if you rebuild the container or whatever, you could lose it, but at least locally in the container, in that nice little encapsulated environment, it works because you have the exact version working. Now, if you start pulling web resources pull things outside the container, bets are off because those things would change. But it's as if you did the analysis on computer, you unplugged it, put it in the mail, and fax it, sent it to your friend, and they plugged it in and did it, right, and used it. That's basically what's happening here. It's just in kind of a nice virtual way that's practical. At least that's the idea.
I had a quick question.
Sure.
So I like this. I think this is really cool. I'm frustrated when I don't have code for even like data science papers. If I'm reading something about machine learning, I'd really like to be able to look at their code. But that being said, it's already difficult for people to use something easy like GitHub. All they have to do is push up their code. Maybe this isn't a question for this talk, but how do you step people towards, it is a little bit past GitHub. They do have to put in more effort than just, making a repository and posting up their code. How do you step people towards kind of this containerization, which is definitely more complete and more reproducible than just having?
Yeah, no, it's a great question. And I'll address it a little at the end. What I'll say now, since we have about 10 minutes left here, and I don't have that much more to talk about, but yeah. So I don't think it's actually much harder than putting something in GitHub or something like that. Or any of the analysis is probably much harder than actually containerizing the analysis typically, I would say. My pet peeve is that you need an incentive structure, right? That's the only way this stuff gets done. And you actually get a fair amount of pushback, and you can get some pushback even spending time talking about this stuff or trying to write a manuscript and get it published on this stuff, because people don't like to talk a big game about, oh, we love reproducibility, but if half the journals or majority of journals still don't even require you submit code, and if they do, no one actually checks it to see if it works. And part of this is understandable. No one certainly peer reviews any of this, and that's understandable. There is no incentive structure set up for it. Part of the peer review thing is that you don't have time to make someone's horrible code work, and hopefully this helps solve it. I would like to personally see the pipe dream is you would have, say, a journal require that you containerize an analysis along with the paper, and that you have to get some institutional players in there and some journals to play along with this. But that's kind of my pipe dream. But I think the economists would say you've got to set up an incentive structure to get people to do this, because there is no incentive. There's no incentive structure for me ever doing any writing my code ever or sharing it. Doesn't actually matter really. I mean, there's a tertiary benefit of you get a good reputation and you can sleep well at night. I mean, hopefully you're doing good science, but the real incentive structure, I think, is kind of lacking in that area. So.
NSF is getting more serious about data management plans. So,
yeah.
I mean, NSF, if they start telling people that this is part of your data management plan to say what you're going to do, I guess they don't really enforce it, but at least they can tell you to do it.
Yeah, no, it's good. And hopefully, and none of this technology I'm presenting here is new. It's been around for 5 years, and other people have said this stuff too. But it's even hard to get people to look at putting out a manuscript on this kind of thing, because no one cares. It seems like no one, it's very frustrating sometimes, but yeah. But I think that what you said, someone like NSF saying, we're going to set up a repository. NIH does this. NIH has GEO, right? They can deal with this. They have the facilities. It's just we need these institutional players to help us with this, because they could set up a repository and to host these kind of things and force people. If you get funded by NIH, you have to have some kind of really actually reproducible thing. And some journals do have, quote, an editor for reproducibility, but I've never heard a peep out of them for anything I've ever submitted. So, okay, in the last couple minutes here, let me just touch on a couple little things here, and then we'll open it up hopefully in the last couple seconds. So the last thing I want to advocate for here is intermediate caching of results. And so you can containerize any analysis. The nice thing about this whole approach is I'm not writing a prescriptive paper telling you should organize your code in this way and put this file in this folder and name it this way. And people write those papers. It's very personal how you do your analysis, and you can do any kind of analysis you want. Not every kind of analysis is a good kind of analysis to do, but one thing I would advocate for is caching intermediate results. So here I have kind of a flow chart. You take your raw data, you process it in some process data, and you get some output and results, right? And if I just give you one script to do all this, my only entry point to this analysis is the raw data. I have to go through the raw data processing, then through the process data processing, and then I finally get the output. And so technically I can share that with you, and technically it's reproducible. But if it takes 10 days to process my, my RNA-seq counts or whatever, it's not actually reproducible. And what you really want to be doing is caching or saving intermediate results. So I want to, after I've processed my raw data, I want to have a cache version of that. And then after I've processed my process, done some processing on it, I want to cache that and save it. And I want to save my outputs so that if someone comes along, they have multiple entry points into the analysis. I can jump in after your raw data. I don't have to sit for 10 days and watch your RNA-seq, be counted or whatever. And I can jump in right before your final plots and play around with your plotting code. Or I can just look at your results. Again, this is not something particularly new, but containerization actually makes a really nice platform for this, because you can encapsulate any kind of analysis here. So I can encapsulate all my intermediate versions of my data, and I can encapsulate them together with the processing scripts. And if you kind of chunk up your analysis in this way, you can actually make it easy for people who have entry points in your data to actually just jump in at various points, play around with the code at a local level, see what happens, and not have to parse through this whole thing or rerun the whole analysis. So I'll basically end here. Some final thoughts, and then we have a couple minutes. So we have our goals, reproducibility. Some other benefits of doing this stuff, security. Even when you get code, if you're asked, I think it's almost unreasonable for an editor to ask you to take third-party code from some person and run it on your computer. That's a big problem, and there are many institutions that do not want that and would not be happy if they knew that was happening. So the nice thing about containerization is all encapsulated. So I'm running their code on their thing. It's not a security issue, and it's not even cluttering up my workspace with their code, which is producing all this intermediate stuff I don't want. And when I close the container, it goes away. This can be a nice tool for teaching. One could imagine that there's a question here about, is it easier to help students install software, or is it easier to have them just install Docker and then you give them the environment where they do all their analysis and it's perfectly set up? But at least you could talk about it, and it gives a nice way of talking about reproducibility, which is certainly warranted. One of the kind of hidden benefits of going through this is hopefully it forces some code review. It forces you to go back and think about the structure of your code a little bit. It forces you at least to make sure that when I put my code in this container, everything's in there. So it actually runs from start to finish, and everything I'm sharing actually is complete and can run it, which isn't always the case. And you can use this with all these kind of popular code sharing, GitHub code sharing platforms, and all. There's lots of cool software engineering tools for this. Leah brought up data and code rights. For example, MATLAB, they claim they can do it. I'd be curious. It is an issue. Certainly data rights can be an issue. And then Dan Vasily brought up, and Sudeep brought up some issues about archiving and storage, right? So these things can, that simple image I shared was 5 gigs. The kind of interactive, flashy one is about 5 gigabytes. Not too bad. really need something. So there is Docker Hub where you can share these. They're really not interested in posting the world's scientific data. We would really like some kind of institutional players to put some stuff, universities, journals, NIH, someone like that, to put some of the stuff out there, because these things can get a little bit more unwieldy than just say code. So I'll end it there. We have a little manuscript we wrote up on this. Here's our page on it. You can download the examples and the code and everything there. But I'll stop here, and we can open it up to any discussion if people want to have that. Questions, comments?
I was just going to say, I'm a big fan of the notebook environment for sure. I've been ever since I've been teaching, I use purely like Jupyter notebooks, and as far as like Google Colaboratory goes, that's great. There's also for anyone that doesn't know, we have a service hosted here at William & Mary. It's called Jupyter Hub. You don't need anything special. It's just I'll put the link in the chat for anyone that wants it. But it's great because whether I'm working here on my computer at home or my laptop, or if I want to go into the library or wherever I am, I can access all my code, my data. I like the fact that someone else is sort of storing it all for me. Of course, I don't ever trust that entirely. I do make periodic, local backups and stuff like that. But it's funny because I had like an issue a few semesters ago with students getting wrong answers for something, and it took me a while to track down what it was, and it was simply just an out-of-date library, some random number generator. There was a minor change, so their dice roll was a little different than mine, right?
Yeah.
And so this kind of stuff is really great. It took way too long to troubleshoot like a simple problem like
that. So I'll tell a short story related to that. This is a paper we were working on. What the initial impetus for this was, the paper got sent off for review. Everything worked. Great results. Came back for review. They had a couple things they wanted. Reran the exact scripts. Different answer.
Yep.
Totally different answer. Turns out dependency had changed, and not fun to get as a different answer when you rerun your exact same code in the middle of a review of paper. But so that was kind of the impetus to make sure this stuff actually works. So yeah, I think it's really common to have that kind of thing happen. I mean, there's a bunch of famous examples of the. Even for example, what was the one about that the econ paper where they made some mistake in an Excel notebook or something, which is, and this doesn't protect against that, but at least you could play around with it, Yeah.
When I'm teaching programming, I always make the point that the computer is always right. And
it did exactly what you told
happened
it
once
to.
to me that the computer was wrong, but only